The differential equation used to model radioactive decay is based entirely on this one sentence here. The rate of decay of a radioactive substance is proportional to the mass of radioactive substance. Alright, so what does proportional mean? So here's a nice example. If you live in most of the world, you measure your height in centimeters. However, you could also live in a country where you measure your height based on the length of a dead king's foot, in which case you measure your height in feet. Now, you're only one height, no matter where you are, no matter what country you're in, and so your height in centimeters is proportional to your height in feet. Meaning, if you take your height in centimeters, which is some number of centimeters, you can multiply that number of centimeters times a proportionality constant in order to convert your height in centimeters to your equivalent height in feet, which will be a different number. Alright, so that's what proportional means. It really means you take some quantity and it's related to some other quantity by multiplying by some constant. That's it. Alright, so in radioactive decay, we have the rate of decay. So the rate of decay, that's going to mean Q prime. And so we're using Q here. So Q of T for quantity. And that's going to be, let's say, kilograms. Then you have T for time. Typically that can be years. So T for time. Quantity of radioactive substance. Pardon my slowness there. Alright, so we have the rate of decay of a radioactive substance. So rate, that's going to be a derivative. So we have dq dt is equal to, proportional, so there's some constant of proportionality, I'm going to call it K, to the mass of radioactive substance. So that's going to be Q. And now there's one more thing we'd like to add here. I left a space. We normally put a negative sign there because we want K to be a positive number. Alright, so in this case we're going to have K is greater than 0. It's the constant of proportionality. So right, if you have a certain amount of radioactive substance, then a certain amount of it is going to disappear, a certain amount of time, and that's related to this value K. The reason we want K to be greater than 0 is it's a little annoying to have negative constants hanging around. And so if K is positive, we want this negative sign so that dq over dt, let me fix that, dt is less than 0 when Q of t is greater than 0, meaning positive mass. Right, and that's a pretty reasonable assumption. If you have a quantity of a radioactive substance, there's going to be a positive mass of it. You don't have negative masses of radioactive substances. So right, if Q of t starts out as positive, then this Q here is positive. The K attached to it is also positive. So you get a negative times a positive times a positive. The whole thing ends up being negative. Then that means dq dt is negative. And if dq dt is negative, it means, radioactive substance is decreasing in mass, right? Negative derivative. Right, and that's what we want. When it decays, a certain amount of it is turning into something else. All right, so that's what proportional means. This is the differential equation. We want K to be positive because it's just a little more convenient when you're doing all the algebra. But if we want K to be positive, we need that negative sign because we want the amount of radioactive substance to be decreasing over time. And this all works out because we also assume that the amount of radioactive substance is a positive quantity. Alright, so next we'll do some examples with this that you typically get in your homeworks.